This video is going to cover the 2.1 warm-up and then the notes for 2.2. So in 2.1, we talked all about quadratic functions, how to graph them and find the information out about it, like the vertex, the intercepts, the max and min, and then any additional points that we might need. So this first example is going to ask you to find the vertex. To do that, when the equation is in standard form, which this one is, we would take the opposite of what follows the x, which is 4, and then the number that's left by itself, we'd keep the sign. So this vertex is 4, 5. If it had asked for it, then our axis of symmetry comes from that, and that is x equals the h, or in this case 4. Then it says find the intercepts. So to find my x-intercept, I'm going to plug 0 in for the f of x, which is my y. I'm going to subtract the 5, and I get -5 equals x minus 4 squared. When I go to square root both sides of this equation, I get a square root of a negative number, which is not a real number, it's an imaginary number, which means there is no x-intercepts. Then we go to our y-intercepts, and for this, we plug 0 in for x. And I get y is 21. Then it asks me for my max and my min, because this is a parabola that opens upward, and I know that because it's positive here. I know that this has a minimum, and the minimum is the k, or the y coordinate of my vertex. So the minimum here is 5. So if we plot what we have already, we've got a vertex at 4, 5, and then we've got a y-intercept all the way up at 21. So I don't know, somewhere way up here, 0, 21. So I want to plot some additional points because I didn't have enough to go on. I'm going to go left and right of my vertex x coordinates. So I'm going to plug in 3 and I'm going to plug in 5. 3 minus 4 squared plus 5, and then 5 minus 4 squared plus 5. I get -1 squared plus 5, 1 plus 5, which is 6, and then 1 squared plus 5, or 1 plus 5, which is also 6. And that's what we should have seen happen because we picked points the same distance. So this is 3, 6, and this is 5, 6. So now I can plot those points. I get these 2 points here, and then I'm going to connect them. I can use that y-intercept. It's going off my graph, but I can use it to give myself one additional guide point. Number 5 says to find the vertex of the function f of x equals 4x squared minus 4x plus 21. So I'm actually going to do this 2 ways so that we practice both methods. The first is doing negative b over 2a. So if I have the choice, which I do here, I would go, if it's in quadratic form, which this is, and I know that because of the squared and the non-squared x, I would probably use negative b over 2a. So your a is 4 and your b is -4. Negative 4 over 2 times 4 gives me a positive 4 over 8, or 1/2. And that's the x coordinate of my vertex. So then I'm going to take that and plug it back in. Y equals 4, 1/2 squared minus 4 times 1/2 plus 21. I get y equals 4 times 1/4 minus 4/2 plus 21. Y equals, this is 1 minus 2 plus 21, -1 plus 21, which is 20. So the y coordinate of my vertex is 20. So that's one way to get it. We're going to practice complete the square just because you're going to need it. So I'm going to walk through those steps. So the first thing I'm going to do is just rewrite my function down here so it's a little bit clearer. Okay, so when I'm completing the square, the first step is to group the first 2 terms together. Then I want to look at the a, and if it's not 1, I've got to take it out. So for this, I've got to take out a 4 off the x squared term and off the b term, so this becomes minus x. I'm going to leave this space because I'm going to fill it in, plus 21 stays to the outside. Then I'm going to take the b, which in this case is -1. I'm going to ignore the sign because I'm going to end up squaring it. So that's b, which is 1, divided by 2, and then square it, and I get 1/4. That's what I'm adding in here. And then normally I would subtract it from the outside here, but I've got to take into account that I took something out here, so I'm going to multiply it by that number first, and I get -1. So instead of subtracting 1/4, I'm actually going to subtract 1. This becomes 4x squared minus x plus 1/4 plus 20 equals f of x. Now I want to factor what's inside the parentheses that I just made into the perfect square. So f of x equals 4. Square root of x squared is x. Square root of 1/4 is 1/2. Sign from this middle term, which is negative. Put it in parentheses, square it, plus 20. Now this equation is in standard form, and I can get my vertex, which is the opposite of what follows x, and then the k that's by itself on the outside. And these should match. So again, on your quiz, you're going to be asked to put a quadratic form into standard form by completing the square. And then you'll get another question in which you'll have the choice if you want to do it that way or if you want to do the -b over 2a. Okay, chapter 2 is called Polynomial and Rational Functions. So we, in this section, are going to learn how to graph functions that are not your normal parabolas. These will all be continuous graphs. A continuous graph is a polynomial function of degree 2 or higher, and they have graphs that are smooth and continuous. There's only rounded curves, so there's no sharp points like in an absolute value function or in some of our piecewise functions. There's no sharp corners, and there's no breaks. So your curves can be drawn from one end to the other without lifting your pencil or your stylus. These are examples of what you should see and what you shouldn't see. So on the top, this is a graph of a polynomial function. Notice this is smooth and continuous. It doesn't have any breaks in each of these. And then this is not graphs of polynomial functions. There's a break here, so that wouldn't work. And then this one has sharp corners, which also won't happen. So the first thing you're going to do is if you just have a monomial, and a monomial is one polynomial with a single term, so something like x to the third, x to the fourth, x to the fifth, x to the sixth, something like that, just a single term. And the rules are here. If your n, which is your exponent, is even, like squared, raised to the fourth, sixth, eighth, and so on and so forth, then the graph resembles that of f of x equals x squared, or my parabola. If the n is odd, then it resembles that of an x cubed, which goes up to the right and down to the left. The greater the value of n, the flatter the graph is near the origin. So what this means basically is that if I were to just compare, let's say, f of x equals x squared and f of x equals x to the sixth. So if I were to actually plot points here, if I plug in 0 into each of those, I get 0, 0. If I plug in 1 into each of these, I also get the same points, 1, 1. Now it would increase faster for the higher exponent, but also what happens in between these functions, in between the segment that is in between 0 and 1, is it flattens. So if it's x squared, let's say, and I plug in a negative, let's say I plug in a 0.1, I'd get, or even just 1/2. 1/2 squared, which is 1/4. So if I'm looking at my squared function and I go to 1/2, my x value is 1/2, my y is 1/4. But if I go to my x to the sixth function and I plug in 1/2, now I'm doing 1/2 times 1/2 times 1/2 times 1/2 6 times. So this is 2, 4, 8, 16, 32, 64. So now my point is even closer to the x-axis. You don't really need to graph these exact points. You just need to know that something with a higher exponent is going to be flatter or closer to your axis than something with a lower exponent. Okay, so that's what it means by flatter. It would continue on closer to the axis the higher the exponent it is. Same goes for a cubic function. So if my cubic function goes from 0 to 1, 1, and 1, negative 1, my normal cubic function takes on that shape, whereas the higher the exponent, the flatter it's going to get through your origin, and then it will increase faster once you get past 1. So given that information, we're going to sketch our graphs. When you look at this function, my monomial has just one term with a variable. A is x to the 7th, which is odd. So we're going to say that this resembles our x to the 3rd function. And the plus 1 is a shift up 1 unit. So these are just approximations. I know it'd be kind of flatter around my my y-intercept, or that 0, 1. For b, now it's raised to the 4th power, so this is going to resemble a parabola. The shift this time is -1, which means it shifts to the right 1. And then again, it takes the shape of my normal parabola. So these are still just based on transformations, not exact beside your vertex. Okay, now we're gonna find what's called the end behavior of a polynomial function. The end behavior is what's happening on the end and the beginning of my graph. So on the left side and the right side, which direction are those arrows pointing? And this has a lot of text on it, but basically you want to focus on the highest exponent is the degree of the polynomial. So we want to look at the highest exponent, which we're going to call n. So it's sometimes first, but sometimes it's not. So you might want to reorder yours so that the highest exponent comes first. And then there's 2 cases at the beginning. If that highest exponent is odd, one of my arrows is pointing up and one is pointing down. If the number on the front of the exponent is positive, then it rises right and it falls left. If the number on the front of that odd exponent is negative, then it rises left and falls right. So rises right, falls left, or rises left, falls right, based on it being odd, and then if it's positive or negative. For the n being even, so if the highest exponent is even, they will either both point up or both point down, just like a parabola. If the a, or the number on the front of it, is positive, then they're both going to point up. Both are up this time. If the n is or the a is negative, so the number on the front is negative, then they both point down. So again, we're going to look for the highest exponent and the sign in front of it. So if I had 3x squared minus 4x plus 10x to the 3rd minus 5x to the 4th, I'm going to first look at all of the numbers that are there, find the highest exponent, which is here, identify if it's even or odd. This time it's even, which means they're both going to point up or they're both going to point down. And then I look at the coefficient on the front of that variable and figure if it's positive or negative. This is negative, and if it's even and negative, they both point down. Or it falls right and falls left. So this just sums up what we talked about. The odd degree polynomials have opposite behavior. If A is positive, then the graph falls left, rises right. If A is negative, it rises left and falls right. The even degree has the same behavior. If it's positive, both ends point up. If it's negative, both ends point down. So here's an example. Use the leading coefficient test to determine the end behavior of the graph of f of x equals negative 3x to the third minus 4x plus 7. First step, identify your highest exponent, which is the 3. Looking at that entire term, the odd exponent tells me they're going to have different behaviors. One's up, one's down. Then I look at the negative on the front, and this tells you it's going to rise left and fall right. The next thing we're going to determine about a graph are the zeros of that function. We've talked about this a lot. Remember that a zero is the same thing as a root or a solution or the x-intercept. So we would set the polynomial function set equal to 0. So we're going to replace f of x with 0. And then for each real root of the polynomial, it appears as an x-intercept of the graph of the polynomial function. So zeros, roots, and solutions are all the same thing, and it is where the graph is going to cross the x-axis. All right, so we're going to use example 3 to find all the zeros of x to the third plus 2x squared minus 4x minus 8 equals 0. Initially, you would actually see this as written as f of x, and you would know to substitute 0 in there, but we're just going to skip that step and go straight to setting it equal to 0. So most of the time, you're going to have to factor these. When you look at this polynomial, hopefully you realize that there's 4 terms. We're going to factor by grouping. So I'm going to group these together and these two together. I'm going to look to see what I can take out of the first set of the parentheses, which is x squared. And I get x plus 2. And then I look at the second set of parentheses, keeping in mind that I want the parentheses to be the same. So I can take out a negative 4. And I get x plus 2. If you had taken out a positive 4, you would have needed to remember to go back and switch your signs. Now I get x plus 2 times x squared minus 4. And that can actually be factored one more time. I'd get x plus 2, x plus 2, and x minus 2 because it's the difference of 2 squares. So because if any one of those parentheses is equal to 0, the entire function is equal to 0, we split them and solve them. So this first 0 is negative 2. I get a negative 2 again, which in a little bit you'll understand why that's important, and then 2. So when I'm listing the zeros of the function, I'm just giving the x values negative 2 and 2. Okay, so this is why it's important if you see a root twice. The multiplicity of the x-intercepts. If a root occurs more than once, then the multiplicity is the number of times a root occurs. So if you look back on the example we just had, we had negative 2, and 2, which means the multiplicity on negative 2 is actually 2 because there are 2 times in which that's an answer. If the root occurs an even amount of times, then the graph hits the x-axis and turns at that point. So if I had a point at negative 2, I don't know what the end behavior is, but let's say it comes from the bottom, it would hit and turn at that point. Whereas If the root occurs an odd number of times, like 1 or this 2 here, then it's actually going to cross through the graph at that point, not bounce. So even multiplicity bounces, odd multiplicity crosses through. Okay, the turning points of a function is how many times the function changes direction. If a function is a polynomial function of degree n, again n being the highest degree, then the graph has at most n minus 1 turning points. So notice it says at most. It can have less than n minus 1 turning points if one of your roots is actually an imaginary root, but it cannot have more than n minus 1. So in the example that's here, this actually says, it's hard to read, but it says x to the 5th minus 6x to the 3rd plus 8x plus 1. So the highest exponent or degree is 5, which means the most amount of turns this function can have is n minus 1 or 5 minus 1, which is 4. So if you look at this graph, you're seeing it go from increasing to decreasing. That's 1 turning point. From decreasing to increasing, that's your second turning point. Increasing to decreasing again, that's the third, and decreasing to increasing again, that's the fourth turning point. So this is really helpful to kind of confirm your graph, or to use in a matching scenario where you've got to match these graphs. Anything that had something like 5 as its exponent couldn't have more than 4 turns. Okay, so now we're going to put it all together. Example 4 says find the zeros, determine the multiplicity of each zero, determine the maximum number of turning points, and then use a graphing utility to verify. So hopefully this looks familiar because we've actually already found the zeros. If I set this equal to 0, I know I have to factor it by grouping. I took out the x squared here. Took out the negative 4, x plus 2, x squared minus 4, which becomes x plus 2, x plus 2, x minus 2, which means my zeros were negative 2, negative 2, and 2. So when I list my zeros, it is negative 2 with a multiplicity of 2, so we can put a little 2 and circle it. On your web assign, it will actually ask you for the multiplicity, and then positive 2. So those are your zeros. Then it says determine the number or maximum number of turning points. So I look at my highest exponent, which is 3. 3 minus 1 is 2, which means there are a max of 2 turning points. And then it says use a graphing utility to verify. So I'm going to take out my graphing utility and I'm going to graph it and pull the picture in. So I've graphed on my app. I typed in x to the 3rd plus 2x squared minus 4x minus 8. And you can see from this graph that there's a 0 here and here at negative 2 and positive 2. And there's 1, 2 turning points. And because the multiplicity of that negative 2 is 2, we see that it bounces off of 2. Because the multiplicity of positive 2 is 1, we see that it crosses through 1. All right, so a quick reminder, we did this a lot with the last chapter, but a way to find your zeros, remember that if you're using your handheld like a TI-83 or 84, that you can graph your function. You can go to second trace and then pick 0 from your list, and then set up your left bound and your right bound. So you'll set up the left bound, the right bound, and then guess. It will take you to that point, and then you'll do it again here. Left bound, right bound, guess, and it will take you to that 0 there. If they are whole numbers, you can also see them in your chart or your table, but you won't see all your decimals, which you will have. Okay, so we're gonna just wrap it up, put it all together. This is your strategy for graphing these by hand. So no longer are we gonna do it with the graphing utility, we're also gonna do it by hand. The first thing you want to do is use your leading coefficient test to figure out your end behavior. So remember, this is if your exponent is even and positive, then they both point up. Even and negative, they both point down. Odd and positive, it rises right, falls left. And odd and negative, it rises left and falls right. You can find your x-intercepts or your zeros by setting f of x equal to 0. And then look at your multiplicity. If the number is even, then it touches the graph and turns around. If it's odd, it crosses through the graph. The bigger your exponent is, the bigger the multiplicity is, the flatter it is around the graph. But you won't really see that too much as long as you take your turns at the right spot. You can find your x-intercept to help you out with an additional point. You can use your symmetry, y-axis or origin symmetry, to help you confirm your graph. And then you always want to double check your max turning points by doing the n-1 and making sure you haven't turned it too many times. All right, so we're going to put it together with this one. Graph f of x equals x to the fourth minus 4x squared using what you've learned in this section. So let's start with our end behavior. I'm going to take my function. I'm going to look at the highest exponent, which is to the fourth. I'm going to look at the number on the front of it, which is positive. So positive and even means both my arrows are pointing up. Then I'm going to find my zeros. So I'm going to say 0 equals x to the fourth minus 4x to the second. I can take out an x to the second, and I get x to the second minus fourth, which can be factored one step further because it's a difference of two squares. And then I would solve each of these. Now when I go to square root, remember your even root property says plus and minus. And while it's not going to change the value on that 0, it does mean that there are 2 zeros. So the multiplicity there is 2. Then I get x equals negative 2, and then I get x equals positive 2. So my zeros are negative 2, multiplicity of 1, 0, multiplicity of 2, and 2, multiplicity of 1. So I've got both up, zeros. Then I can find my y-intercept by plugging 0 in for x. So y equals 0 to the fourth minus 4, which makes sense because I already got this for my x-intercept. Y would equal 0. So now let's go to our graph and graph what we have so far. Okay, so I just made our axis a little bit brighter so you can see it. I'm going to plot my zeros at negative 2, 0, and positive 2. I know my arrows point up in both these directions. I know it crosses through here, comes back up, bounces here, goes back down, and comes back up again. Now what I don't know is how far down those 2 points go, and to confirm that, I'm going to actually plug in values. So it's easy with these. The only x values that are in between there are negative 1 and 1. If I plug in negative 1, I get negative 3. So that part of my graph should actually go a little bit further down to negative 3. Now, if I don't know anything about symmetry, I can plug in positive 1 as well and see what happens there. And I also get negative 3. But the benefit of knowing about symmetry is that if I take a negative x and I plug it into both of these, it's going to go back positive, which means that this is symmetric to the y-axis, and it confirms my graph. The max turning points would have been 3. This is 1 turning point, 2 turning point, 3. So it makes sense with everything else that we found. And last one. So we're going to do the same thing again, follow the same pattern so you get used to the steps. And I'm going to start with my end behavior. This time, the highest exponent is odd, but it's positive. Positive and odd means it falls left and it rises right. Then I'm going to find my zeros. 0 equals x to the third minus 9x squared. I can take out the x squared. Set them each equal to 0. I get x equals plus and minus the square root of 0. So again, the 0 is 0, but the multiplicity is 2. And here x equals 9 with a multiplicity of 1. If I wanted to try my y-intercept, I would plug x in, and the same thing's going to happen. I get y is 0. So far I only have 0, 0, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9, 0. I know it falls left. I know it rises right, and I know it bounces off the 0, goes down, and has to come back up to cross through that 9. Now, I don't know how far down to go. You can pick a point somewhere in between. 9, the distance from 0 to 9, I'm not going to plug in 4.5. So maybe I just want to plug in 4 to see how far down it goes. I would get 4 to the third minus 9 times 4 to the second. So 64 minus 9 times 16. 64 minus 144, which is negative 80. So this is going way down. You don't have to plot that exact point. You can actually write for negative 80 to show where you were trying to bring your graph to. But what this does tell us is that I know it's going to go down way further than I initially assumed. This should be a smooth curve, so I don't want it to be sharp. I want it to go all the way down, and I want it to come back up and cross through 9, 0. So as you go to do your graphs, please make sure you're graphing these by hand on WebAssign. Don't just use WebAssign, and don't just use your graphing utility. On the quiz and on the test, you're going to have to graph these by hand. You're going to have to give all this individual information, your end behavior, your zeros, your intercepts, and then you're going to have to graph it with your multiplicity. So please make sure you're graphing these by hand for practice. You can use the rest of the time in class to start that WebAssign assignment, and then tomorrow I'll go over it. Have a great day, guys.